All the cryptography that Bitcoin relies on today is hinging on a single cryptographic problem. And if that problem breaks in any way, not just if a quantum computer breaks it, it would be really nice to have something a little more conservative to fall back on, something that will help us preserve the integrity of the UTXO set over very large spans of time.
Conduition, thank you so much for being here today. I think, if I'm not mistaken, this is likely your first kind of big video interview.
I believe so, yeah. I think the only time I've ever appeared live was also at Bitcoin Vegas, but that was at a relatively niche talk.
Fair enough. And I assume you were talking about quantum, which is what we'll be talking about today.
Certainly. We
have a very special episode planned today. You know it's special because we have the whiteboard assistants to help us out. We're going to be we will be deep diving into shrinks, which in my opinion is kind of the leading post-quantum signature scheme, most likely at this moment, the kind of front-running contender to make it into Bitcoin, as sort of the post-quantum signature scheme that we'll likely use.
Very excited to hear that.
Yeah, that is my point of view.
I'm excited to hear excitement about the scheme that we're working on.
100%. And I'm, obviously I think that this was, original. Well, let's actually back up. I'd love to get a little bit of your story of how you got so deep into this work. You're now, I think by the time this comes out, it will be announced that you're a co-author on the BIP proposing op shrinks. Is that what we're calling this?
The initial thing that we're going to be putting out is going to be the signature specification of shrinks. And that's going to be a self-contained, purely cryptographic BIP, kind of like how BIP 340 was for Schnorr. So we're not immediately going to be proposing a consensus change rule to include this. That's going to be part of a follow-up series of BIPs, because there's actually a series that we need to do. Shrinks itself is agnostic to how it is deployed in consensus.
How many BIPs in total will you guys need to write to have sort of like a comprehensive
That's a great question.
TQ signature shrink scheme? And I know it's kind of a trick question because I know enough about this process from BIP 360 to know it's a trick question, but curious.
It's a complicated matter because you also have interplay with competitive proposals like P2MR and P2TRV2 and P2TRH. And then you have the question of how does this interleave with unrelated proposals, things that aren't related to quantum at all, like Fabian's CISA proposal, CISA, and Great Script Restoration.
Like basically how this interacts with other parts of the protocol that might need their own separate BIPs.
Exactly. So that's still a question that we're sorting out across different working groups.
Do you have an idea? But so this will be the signature specification. Do you have any idea what the next BIP after that will be? Like what's the next step thereafter?
Our current draft plan is to propose a new TapScript leaf version, which overloads opchecksig in such a way that you can execute either BIP 340 signatures or shrinks signature verification.
Okay.
Yeah.
And so just again, to back up on your sort of personal history around this, I think I came across your name, it was probably like a year and a half ago. And you were sort of kind of casually blogging about this topic, but you were already blogging about post-quantum pretty significantly. Would you mind sharing a little bit how you got into sort of tell us about your blog. I mean, this was kind of how you sort of made your name for yourself in this space, was blogging about this topic. And now here you are co-authoring a BIP with the Jonas Nick Blockstream team. I'd love to hear a little bit about how the blog came to be and what the intention of your blog was.
Well, I've worked in the orbit of Bitcoin for a long time, and it was I think it was 2022 or 2023. I decided to start pursuing Bitcoin development a little more actively and learn more about the cryptography specifically. And I did some various works on my blog, mostly aimed at building a portfolio that I can point to say, hey, look, I know what I'm doing, so that I could get hired by companies.
Smart.
I did that for a little while. I did some odd jobs. And I think it was in the end of 2024 or thereabouts, I started hearing about quantum computing and quantum cryptography. And I was like, what's that? So I started looking into it. And I fell down a little bit of a rabbit hole learning about hash-based signatures. You might recall my first ever blog post regarding anything post-quantum at all was a survey of different hash-based signature schemes, going through the history of like Lamport, Winternitz signatures, and all the way through to modern Sphinx.
And that was pretty progressive at the time. I mean, this was before Blockstream or Jonas had written any of their kind of papers on hash-based signatures. I mean, you were really kind of the first to be, at least in writing, diving into this topic.
I'm late when it comes to the post-quantum cryptography game in the grand scheme of things.
Outside of Bitcoin.
In the Bitcoin world, I'm not sure. I'm sure there were people working on it well before me. It only became popular quite recently because of developments in the field of quantum computing. And then people started to worry a little more,
How did you start working with Jonas? How did you start collaborating with the Blockstream team?
It was in, I believe, the end of 2025. I had been in a coding dungeon for the last 9 months building a prototype called slhvk. It's I believe, and I'm happy to be corrected on this, but I believe this is the world's fastest implementation of Sphinx, at least the CPU-bound implementation. And this was the result of a lot of pain and a lot of sweat and tears. It came out, my blog post on slhvk came out right around the same time that Jonas and Mikhail published their survey of hash-based signatures for Bitcoin.
Okay. And not to go down too much of a sidebar here, but I have to ask, what makes this particular implementation of Sphinx so fast? Like, what is the distinction that supports the speed of verification of Sphinx signatures?
Actually, it's not verification. My implementation is the fastest signing and key generation.
Oh, it's for signing. Okay.
And part of my part of the work that I did there was surveying which performance improvements affect which algorithms the best. It actually turns out that specific optimizations are better for signing and keygen, and others are better for verification, which is really useful if we want to do hash-based signatures on Bitcoin.
So around the same time was when Jonas published hash-based signatures for Bitcoin, the sort of paper that he put out with Blockstream.
Yes.
And did you, I think you had told me that he posted it on Delving, or you engaged with comments or something along those lines, and it probably became pretty clear that you were pretty deep in this research as well.
Well, we riffed on the different ideas for how you'd manage state in a scheme like Shrinks, which we'll talk about that in a bit. But we riffed on that for a little bit. I linked him to a couple of my works on hash-based signatures before. And I think it was through contact with people that Jonas knew. He talked to me and invited me to into a working group with him and some other Blockstream folks to work on Shrinks and see how viable we could make it for Bitcoin.
Amazing. This is pretty impressive given the fact that, these are all folks who really studied cryptography. You're a layman.
They're people who inspired me.
Really?
Oh, yeah, absolutely. It's otherworldly to get to meet all of the famous Bitcoiners and cryptographers and developers that I've read about and read works of for many years, and to get to actually talk to them and jam on stuff now is incredibly flattering.
I imagine if Jonas was here, he would say that he was very impressed with the fact that you did not have a, academic cryptography background, and you were sort of a layman coming up and really holding your own in these conversations. So in my opinion, that's sort of equally impressive. So, and I imagine he would agree with me, but we'll see. So I'm curious, was most of your research focused? You've also done some work on isogenies signatures. We're not going to go too far down that rabbit hole today.
It is a hell of a rabbit hole to go down.
It's a hell of a rabbit. We'll have to do a separate isogenies episode at some point.
Anytime.
But the reason why I bring this up is because I'm just curious, was most of your early research around this time really focused on hash-based signatures? And if so, why? Why hash-based signatures, in your opinion?
Well, the thing is that even if quantum computers never appear, hash-based signatures are still a good idea. That's why I was so interested in them.
Oh, explain, please. Why?
Well, all the cryptography that Bitcoin relies on today is hinging on a single cryptographic problem. And if that problem breaks in any way, not just if a quantum computer breaks it, it would be really nice to have something a little more conservative to fall back on. Something that will help us preserve the integrity of the UTXO set over very large spans of time.
Let's just be specific about the specific problem that you're referring to, which is elliptic-curve cryptography potentially being cracked, right?
Precisely.
I mean, there's, in theory, not just quantum that could break this, but, advancements in AI and other things. I know Ethan Haleman, who's, I believe, is also a co-author on the BIP, talks about this often.
Oh, yeah.
So that was a kind of major incentive for specifically hash-based, though, not isogenies or lattice?
I believe isogenies and lattice-based fulfill a different role. I see them and other more cutting-edge post-quantum crypto systems, and I see those as a more long-term solution rather than hash-based signatures, which fill a very different role. They are, in a way, a regression because they lose many features that we have with elliptic curve cryptography. But they give us a feature that no other family of signature schemes give us, which is a more conservative set of assumptions than even Bitcoin itself.
Because it's more conservative than elliptic curve cryptography. Is that
the
argument?
It's more conservative than most of Bitcoin's existing address formats in a way. We can get into that later, but okay. Basically it has to do.
For now.
Yeah, we can get into that.
Interesting. Okay, so hash-based signatures you see as something that, I mean, what I'm hearing is we need hash-based signatures kind of as a backup, in case ECC breaks by some method, doesn't even matter what. And lattice-based and isogenies are maybe something, pending research we can add later. Mm-hmm. What do you think about the argument, adding these signatures after the fact will be too politically difficult, right? Like, can we do multiple upgrades to Bitcoin, adding new signature schemes multiple times, or do we only have one shot at this?
It really depends on how the community of Bitcoin is shaped over time. And that's not really a question I think is answerable today. And I think a lot of it depends upon what we do today. If we have a conservative hash-based signature scheme in our pocket today, or, in the next few years, then it becomes much easier to argue for more cutting-edge crypto systems like isogenies, for instance. Because if the core assumptions of isogeny crypto break, well, it's not such a bad deal because we have hash-based signatures to fall back on. We could, for example, construct an address that has two different spending conditions, one for isogenies and one for hash-based signatures. And if isogenies break, well, we can fall back to hash-based.
Do you think that hash-based is something that also we can just practically get done faster? I mean, do you see lattice and isogenies as something that just needs significantly more research time in order to be kind of hardened enough for Bitcoin?
I can't speak to lattices too much. My understanding of them is somewhat limited. I can say for sure that more research needs to be done into isogeny cryptography before we could confidently deploy it on Bitcoin. Although I am such a fan of isogenies that it's hard for me to say that. Lattices are relatively mature by comparison. They have other problems, which I don't think we should probably get into today. It's a little bit of a tangent.
Okay.
But isogenies absolutely need more time to bake. And I'm excited to bake those cookies.
When, and before we again kind of dive into how the signature scheme actually works, how quickly do you think that, from a technical perspective, politics aside, we could get this PQ signature, specifically shrink, sphinx, some sort of sphinx or hash-based signature? Yeah, how quickly do you think we could get that done in Bitcoin?
Oh, that's a hard question. My optimistic side says 2 years.
Okay.
My pessimistic side says they'll be deployed right before quantum computers appear.
Really?
That's my pessimistic estimate because, yeah.
Oh, man. Okay. So whenever that may be, we'll see. Basically, you're saying like there's a possibility that politically we'll just like wait until the very last second because...
Could very well happen.
Could very well happen. We'll see.
Yeah.
All right. So basically, it sounds like your argument is that Sphinx makes sense because, or some sort of Sphinx-based signature scheme makes sense because they're hash-based and we kind of already trust hashes in Bitcoin. Is that a fair argument?
Yes. The community of Bitcoin is very cryptographically conservative. I think Benedict also said this on your podcast with him. And I watched that and I think it was a very astute observation. And I would agree with it. Yeah, the Bitcoin community is very conservative in their trusting of cryptographic assumptions. And you can very easily see that from the skepticism of lattice-based cryptography, which the rest of the world has happily adopted already.
Okay, so now we'll kind of get into how this all works. Again, when this comes out, I think the bit will probably just be out. That's at least the plan. I'm wondering if you could just sort of first contextualize, how would you describe the relationship between hashes and Sphinx, right? Like, what is Sphinx and like what does that really mean?
Well, Sphinx is a signature scheme. It's called stateless because it is kind of like how Schnorr can be used in that you can generate a key pair, sign many different messages, and you don't need to keep track of anything. All you need is the private key, and you can sign any message, produce a signature, and a verifier can take that signature and your public key and verify that the signature was definitely 100% authored by the person who holds the secret key. And it does so using only one cryptographic primitive, which is a hash function.
So basically, it is like some method of signing that only uses hashes as its sort of, is this the right word? It's like cipher? Is that the right word? I don't know what you would call
A cipher is a way of encrypting data.
Okay.
This is a way of hashing data by essentially passing it through a one-way door that it can't come back from.
Okay. But the hashing is really where like the magic math happens. And the signature is sort of more like the combination of magical mathematic things that we use specifically to execute this action called signing things.
The fundamental idea of hash-based signatures is always to reveal a very specific set of preimages. A preimage, by the way, is just the input to a hash function. So you have a hash, which is the output of running a hash function on a preimage. So you take a certain set of preimages, and maybe also a certain set of other hashes, and you just kind of concatenate them all together, and that forms a signature.
And just for clarity, so Sphinx Plus is used all over the internet, right? Like, this is not a Bitcoin-specific thing. This is not this is not something that was created for digital assets. I think, was it Daniel J. Bernstein who created Sphinx Plus, the signing scheme, and a
number of others, yeah.
Yeah, and I think, tell me if I'm getting this right, that the reason he created Sphinx Plus was he wanted to create a hash-based signature, essentially, that was stateless. Like, that was the intention behind it, is sort of roughly my understanding. Is that why Bitcoiners immediately went to Sphinx Plus as a potential PQ option? Is this sort of statelessness factor?
Well, Sphinx has been around since 2014, I believe, and it came about mostly as an evolution of prior hash-based signature schemes like XMSS. And by combining them together in a specific way, Bernstein and Holsing and a number of other co-authors figured out that you could create a hash-based key pair that has such great signing capacity to be effectively stateless. There's actually no such thing on a technical, if you want to get into the specifics, there's technically no such thing as a stateless hash-based signature scheme. There's just hash-based signature schemes that allow you to make so many signatures as to be effectively stateless.
So, and that's just like a probabilistic thing, right? Like, you have so many the signature budget. Jonas came on the show and described this term, the signature budget, which is you can use like this sort of not infinite by definition, but so many signatures that you don't run out of them, essentially.
Exactly. It's kind of like, and I've used this analogy with Kleenexes before, where you could think of a stateful hash-based signature scheme as a set of Kleenexes. And each time you want to use a signature, you're just taking a Kleenex, blowing your nose, and you're supposed to throw the Kleenex away. If you accidentally reuse the same Kleenex, you explode. And
each signature inside, each of these one-time signatures, what kind of signature, what are the mini signatures inside, right? So if you have Sphinx and it's made up of this like huge number of signatures, what are the little signatures inside called?
Well, there's a number of different subschemes in Sphinx. It depends how deep you want to go into the scheme here.
Okay. Well, let's do a mini review and then maybe we'll get deeper in a moment. But I think it's WOTS?
There's WOTS, which stands for Winternitz one-time signature.
Okay.
There's FORS, which stands for Forest of Random Subsets. And the Winternitz key pairs, those one-time signature key pairs, they are composed into a many-time signature scheme called XMSS, which stands for Extended Merkle Signature Scheme.
So it's sort of a combination of these three schemes, which we might dive into in a little bit more depth, that sort of makes up this Sphinx Plus signature scheme created by DJB.
The nice thing about these signature schemes is exactly that. They're made of a bunch of small building blocks. And if you can understand each individual building block, then it becomes much easier to understand the whole as they're put together.
Can you quickly TLDR why this statelessness feature is so important, right? For Bitcoin specifically. Like, why do we care about signatures being stateless, meaning you have an effectively limitless number of signatures that you can use versus not?
Well, it's beyond Bitcoin even. Tracking state, even just a single number per key pair, just a single counter that increments, that's basically all you need to do. And even doing that is very hard for classical systems, Web 2 systems, Bitcoin systems. It's just a hard problem in general. Because too
many things can go wrong, basically. If you like miscount, you're screwed kind of thing.
Like, imagine if cosmic ray just comes and flips a bit, you're screwed. Imagine if you were to have a backup of your computer and that backup contains that state counter. But on your real computer, it's incremented past that by now. If you restore that backup, the counter resets to where it was before. You end up reusing a Kleenex and you explode. Not great.
Well, and that's actually, I think, a really important key point to explain here, too, is why, losing count of the signatures that you've used is so problematic. Can you maybe explain a little bit why, you explode if you accidentally reuse a signature?
Exactly. Well, the way that Winternitz signatures work on a simple level is basically you reveal a certain set of preimages that are along a set of hash chains. If you reveal one set of preimages in this hash chain, that's fine. The adversary just sees those particular points in each chain. But if you reveal a different set of preimages, then the adversary can see enough preimages to be able to create a signature. Because remember, every hash-based signature is just a set of preimages. And if you know the right preimages, you can forge a signature.
So basically, you kind of de facto leak your private key. You can do signature forging if you lose count or if something goes wrong accidentally with stateful signatures.
Exactly.
Okay. So what are the downsides of stateless signatures? We've kind of covered why stateful signatures kind of make everyone in Bitcoin have the heebie-jeebies. Everyone's kind of scared of stateful signatures, right? You say, we're going to use stateful signatures, everyone kind of freaks out because of this forging risk. But what are the downsides of stateless signatures, or Sphinx Plus specifically?
Major one is, the major one that Bitcoiners are specifically sensitive to is, of course, the size of the signatures. I believe the smallest parameter set that was standardized by NIST for Sphinx was, I think, 7,656 bytes, if I remember correctly. No, 7,856 bytes per signature.
Okay, which is about how much bigger than current elliptic-curve signatures?
Schnorr, about a factor of 100.
Oh, wow.
Yeah.
Okay.
Because Schnorr is 64 bytes.
Maybe the fee maxis will like this. The people who just want to drive up fees and, save the security budget. They'll love Sphinx Plus. They probably love Sphinx Plus signatures.
Oh, 100%.
But everybody else, I guess, who wants to keep Bitcoin nice and cheap to use, this is a big problem.
Exactly. Absent some massive witness discount, which I think would be very unpalatable right now, I don't think those particular size of signatures will ever become common use on Bitcoin.
Do you think that was considered a deal breaker, basically, for Sphinx Plus, or just a concern that somebody was okay, Jonas, we need to figure this out. We need to find a way to optimize this thing and bring the size down, because ultimately hash-based is what we want. How are we going to fix this size problem?
There have been many ways. There's generally two classes of improvements that you can do to Sphinx in order to make its signatures smaller. Number one is you can change the algorithms. So you can change the signing algorithms, which modifies the format of the signature. You can use, for example, WOTS+C, which is a variant.
Smaller.
Yes, and actually that is a scheme that we use in Shrinks. You could use FORS+C, which stands for Fours with compression. You could use PORS or PORS+FP. I can't remember the acronym. I think it's pseudo-random hash to obtain random subsets. This is a replacement for FORS. Anyway, you can swap out the different signature algorithms, and this gives you smaller signatures sometimes.
So one of the ways to optimize Sphinx Plus would be just finding kind of more compressed versions of these mini signatures kind of embedded within the Sphinx Plus signature
Exactly.
scheme.
You're swapping out building blocks, and some of those building blocks have different trade-offs. Like they might have different security assumptions, or they might make signing slower, they might make verification slower, or faster in some cases. The other way of reducing the size of a Sphinx signature is to change the parameter set. And this is something that we do in Shrinks. And it's a hot topic in the classical cryptography world, because in order to do this, you have to make trade-offs. There's no easy free lunch here. The parameters of Sphinx are extremely tunable, and you can optimize them for all kinds of use cases. You can make signing really expensive, but verification really cheap. You can make key generation really fast, but signatures very large. And you can have all these different trade-off dimensions. We optimized the parameter sets that we're choosing for Shrinks such that we trade off a little bit of security budget, where the default Sphinx parameter sets allow you to make up to 2 to the 64 signatures, 2 to the power of 64 signatures, before you drop below this specific security threshold of 128 bits.
So instead of a probabilistically limitless number of signatures to use, which is the case with Sphinx Plus, there's some maybe slightly lower limit. I mean,
exactly.
Is that fair?
If you
but still pretty, still pretty abundant.
You would need to sign repeatedly for more than 100 years in order to exhaust the budget that we allow for shrinks.
Okay, so that's pretty, that seems very reasonable.
Yeah, exactly. And it depends on the implementation.
You shouldn't be reusing your keys anyway, guys.
Exactly. And this is a more than sufficient security budget, we think, for Bitcoiners, even if your signing key is exposed to an attacker that can just repeatedly query it over and over again.
Now, the last time I looked at this, or when I spoke to Jonas, when I had Jonas on the pod, he talked about having a backup, like full probabilistically limitless Sphinx option involved in this situation. Is that still the case?
Yes. And maybe now this is a good time to start transitioning towards how shrinks work specifically, because we've talked a little bit about Sphinx.
Yep.
And maybe now we can put this in the context of shrinks.
Right. Which is the proposed signature.
Exactly.
Scheme. A little confusing, but we're keeping
Exactly.
track.
Shrinks stands for Shrunken Sphinx. And the original idea to this is, of course, Jonas Snick's and Mikhail Kudinov's. This is not my invention. I'm just describing something that they created here. So the idea with shrinks is, okay, we have these stateful signatures, and they're really compact, and they're really efficient. But damn it, state is so annoying. So what if we also attach a Sphinx key to a stateful key, and you just kind of combine them together into one unified scheme? We call this a composite scheme.
Is this something that would be like automated, essentially, this backup, so that like if you run out of your signature budget on the stateful side, then Sphinx is like there to catch you, basically? Or do you have to know when to pull the Sphinx parachute?
From the user's perspective?
From the user's or the wallet's, somebody's perspective, from someone's perspective, anyone's.
From the user's perspective, it would be handled entirely automatically.
By the wallet.
By the wallet. This would be a responsibility of wallet developers to be able to use the correct state for a specific key pair. And I think this is the biggest trade-off with shrinks. Managing that state is very sensitive because if you reuse the state, like I said with the Kleenexes, you kind of expose your secret key.
So you're trusting wallet developers not to screw this up. You have to be really careful now about the wallets that you're using. That's the major trade-off, is that if your wallet developer screws this up, you could lose your money.
Yes, and I foresee a little bit of a Wild West in the early stages of shrinks adoption. However, my hope in the longer term is that we don't need to use shrinks at all, and instead we can use a more fancy signature scheme, like based on isogenies or something, and shrinks can remain in our pocket as a fallback.
Do you think the risk of wallet developers screwing up is like effectively mitigated by the fact that you're going to have a pretty substantive budget, like signature budget for the stateful side as well? Or
well, actually, there's a little bit of nuance to that, because the stateful side has a variable number of signatures in its ammunition belt. The stateful side always has like a fixed capacity, a signing budget, right? Maybe we should break it down here. So the stateful side requires you to maintain a specific counter number, which is basically just a tracker for the number of signatures that you've created. The stateless side does not require that at all. It can be used at any time by any software without having to track state. And the stateful side, depending on how the key is generated initially, it may have a different number of signatures in its ammo belt. So it could go from anywhere from 255 upwards to 1 million.
Oh, so the signature budget is not fixed, basically, with
Yes.
shrinks. It depends on what factors, just how developers choose to configure it.
Exactly. And there are different use cases for different signature budgets. For example, the average end user wallet only really makes maybe 1 or 2 signatures per key pair at most. And this is where we can make an optimization that Jonas pointed out in his first shrinks proposal, which is you can reduce the signing budget of a key in exchange for making signatures much smaller.
Well, I was going to say, is there going to be incentive for wallets to use the smallest possible signature budget?
Absolutely.
Because it'll make the product cheaper for users?
Absolutely. And
will users understand that trade-off?
That's something that it's going to be a matter of education. And I think that'll be a complicated but approachable topic with shrinks.
Fingers crossed.
I hope so.
Yeah.
But the other nice thing about this optimization that Jonas suggested, it's called unbalanced XMSS, by the way. Using an unbalanced XMSS scheme on the stateful side makes signatures grow every time you reuse a key. So it actually disincentivizes address reuse.
Whoa.
I know, right?
Jonas, good one. Okay, I like that. Okay, so that was an intentional fix to solve this incentive problem, basically, of like lowering the signature budget as a way to make things cheaper.
I would say it's a happy byproduct. I'm not sure if it was Jonas's intent or not. He would have to answer that.
Okay.
But it is certainly a happy accident.
What was the other reason what would be another reason to do that?
Smaller signatures.
Just creating smaller signatures in general.
Exactly.
Interesting. Well, that's actually a really good opportunity for us to move into the whiteboarding section of this, right? And now we're talking about Merkle trees and like weird Merkle tree configurations.
Yes, this is where visualization will start to help quite a bit.
This is where visualization is helpful. Okay, so
maybe it's best to start with the shrinks public key format.
The shrinks public key format?
Yes.
Okay.
Yes.
I was going to say, is there anything that we want to whiteboard around Sphinx Plus before we do that? Or do we feel...
Well, we can dive into the stateless Sphinx part of it from the shrinks public key.
Okay.
Yeah.
Great.
Because
Okay.
it starts us off at the highest level and then we can descend from there.
Okay. So I'm just going to hold this.
So the shrinks public key is basically 3 different elements. And I'm going to just block them out here. So this is the shrinks public key. I'm just going to write PK up here. It is 48 bytes total in size. The first element is called PK seed. Oh gosh.
That works.
The second element is called the stateless root. And the third element is called the stateful root.
Okay.
This is basically just 16 random bytes.
Okay.
Generated from a secure RNG.
And just for clarity, so these are like components of the public key? Like how would you describe each of these 3 things? Like what are each of these 3 things?
Each of them is just a 16-byte hash. Or not a hash, I should say. It's a 16-byte value.
Okay.
PK seed is a public but randomly generated byte string which is used to randomize all of the hash function evaluations in the entire scheme. And this is to distinguish hash function evaluations for one public key from hash valuations in a different public key.
Okay.
So that means if I'm verifying a signature with my public key and I run the exact same verification scheme on a signature for my public key, it's going to run completely differently than if I did it for your public key, because you're going to have a completely different PK seed.
Okay. All right. Okay. I'm with you.
Yeah.
SL root.
Yes. Stateless root. This is basically a Sphinx hub key.
Okay.
So we use specifically the NIST standardized version of Sphinx called SLHDSA. We don't use the same parameter set though. We use all the same
signature budget, right? I mean, is that what we mean by parameter set? Okay.
Yes, we have a different parameter set which has different verification costs and signing costs. We try to match it to the standards, but ultimately the main trade-off that we make is that the signature budget is much lower. It goes from 2 to the 64 down to 2 to the 40.
Okay. All right. Yeah. I'm with you.
Stateful root is a FXMSS pub key.
All right. What does that mean? FXMS?
Yes. So when Jonas and Mikhail first proposed shrinks, they proposed using a slightly different format for this key. And instead of using FXMSS at the time, they proposed using something called unbalanced XMSS. This one here, FXMSS, stands for Flexible Extended Merkle Signature Scheme. The flexible part we'll get to in a little bit. Maybe we should talk about the stateless part first.
Okay.
The stateless part is just, as I said, stock Sphinx, NIST standardized with the same algorithms, but a different parameter set. And it is essentially the root of a Merkle tree. Each of these little leaves here in here, and here, and here. Those are the hashes of Winternitz public keys.
Okay.
Yeah,
Winternitz. WOTS+. That's the first time I ever saw it. Winternitz one-time signatures, which we do use in Bitcoin. We use Winternitz one-time signatures in other parts of Bitcoin, or no? Am I inventing that? I think maybe it's BitVM uses it or something. Does that sound right?
I believe I was talking to someone the other day who mentioned that BitVM uses Lamport signatures.
Lamport, excuse me.
I'm not 100% sure.
My bad. No, I think you're right. I think I'm confusing that. Okay. All right.
But yes. And the thing about these Winternitz keys is they actually sign other Merkle trees.
They sign other Merkle trees.
Yes.
Which in that context means what, right? I mean, you're not sending money, right? So what does it mean to sign a Merkle tree?
These are essentially like, do you know how TLS certificates work at all?
No.
Winternitz keys here at this level are used to certify the authenticity of this lower level tree.
Okay.
Right? And the same thing is true for this one and for this one. These each sign their own Merkle trees. But the important part here is that these signatures here, here, and here don't need to be created until they're needed.
Okay. So this is another sort of way, like it's like another efficiency factor or feature. Is that fair?
Yeah. The key observation is that if you were to just generate a very, very large Merkle tree, it would be very expensive to do. And using this construction, you only need to generate the Merkle trees that you need. So this one does the same thing and assigns, another set of Merkle trees down below it.
And just for clarity, so this extended tree sort of represents all of the multiple signatures that you can use. So kind of going back to the statelessness, right, the signature budget issue. These are sort of representations of all of the different signatures that would need to be used over time in order for you to run out of signatures, essentially. Is that right?
Close. There is one final stage that I haven't talked about yet, which is that at the very bottom, after a number of layers in this so-called hypertree, you get to the bottom.
Hypertree being a tree of Merkle trees.
Exactly.
Okay,
it's a tree of XMSS trees, to be more specific. This scheme where you have a bunch of Winternitz keys at the leaves of a Merkle tree, that is XMSS.
Okay.
Each of these is a XMSS tree. And they sign they sign lower level XMSS trees.
Okay.
They certify them as the...
XMSS trees then are signatures, basically.
They are a set of key pairs.
They're a set of key pairs. Okay.
XMSS is just a bunch of Winternitz keys arranged into a Merkle tree.
Okay. So sort of using Merkle trees for the function of signing.
Yeah, exactly. It's kind of like, it's like the Kleenex analogy I used before. Each of these XMSS trees is a set of those one-time use Kleenexes.
Okay. Yeah. Makes sense. All right.
At the bottom, I'm just going to draw another one here. At the bottom of this hypertree, these are also Winternitz keys, but they sign something else. I'm going to draw that as a little square here.
Okay.
This is a 4s key pair. Oh gosh, this marker is hard to draw with. Here we go.
4s.
Yes.
All right.
So down at the bottom, this is a 4s key, which we can get into on another slide. But essentially, 4s is a few time signature scheme. That's distinct from WOTS. WOTS is a one-time signature scheme. It lets you sign at most one message. If you sign 2 different messages, you leak your secret key and you're screwed. 4s allows you to sign multiple messages, just not that many. We're talking about like the single digits before you start to lose too much security.
Okay.
Yeah.
All right. Okay. So that sort of enhances the budget a little bit in this situation?
Massively, yeah.
Okay.
It's a prerequisite for a stateless scheme, I think. Maybe there's a way to do it without 4s or any few-time signature scheme, but I haven't heard of anyone making any concrete proposals for that.
Okay. Can I borrow your marker for a second? Okay. So we have XSMS. Is that correct?
XMSS.
XMSS. Mm-hmm. Which is the kind of one sub-scheme that Sphinx/Shrinks uses.
Exactly.
Then we have Winternitz, one-time signatures, WOTS, which is another sub-scheme that's used, and then 4s. These are the 3 cryptographic subschemes used in this entire construction.
Exactly.
Okay.
And XMSS and Winternitz are closely related here because you can't have XMSS without a one-time signature scheme, and WOTS fulfills that role.
And it sounds like, but tell me if I'm getting this right, and I'm oversimplifying, of course, but they're kind of embedded within one another, right? You have sort of XMSS sort of at the top, and it's filled with Winternitz signatures, and then you have FORS as sort of this like bottom foundational construction that adds this extra layer of statelessness.
Exactly.
I mean, not exactly stateless, but broader, bigger budget. Is that fair?
Here's another way to think of it. In principle, you could have a stateless key pair by just concatenating like trillions of FORS key pairs. But that would be really expensive because you'd have to shove all of them into a really big key pair, or you'd have to commit to all of them in a giant, expensive Merkle tree. So instead, you use this hypertree construction to certify them through a chain of signatures, kind of like how in a TLS certificate, you start with the certificate authority, the root authority at the top, and it certifies other certificates that certify other certificates until you eventually get to the certificate of the website you're trying to connect to.
Okay. All right. Well, interesting. Okay. And so this is for Shrink specifically, right?
This is Sphinx.
Oh, this is Sphinx. We just did Sphinx.
Exactly. Okay. This has been standardized by NIST, and this is used for firmware signing and a number of other high security standards.
So how does Shrinks change this? Like, what about this is different in Shrinks? What are we optimizing here to get Shrinks as more efficient?
If you kind of just take a pillow and cover this half of the board and ignore the stateful part, the stateful root over here, this is just pure FIPS 205 SLH-DSA. This is exactly as specified in the NIST reference document. There is nothing different from it here. The addition that Shrinks makes is all over here with the stateful part.
Oh, I see. Okay, so this is all Sphinx, and then this is basically the addition that serves as sort of the backup stateless option.
Exactly.
That we have just so, God forbid. Although, in theory, am I getting this right? That, like, we hope to never use this. Like, we
the
don't
stateful part? Or you mean the entire key
part?
Yes.
We hope to never use the stateless part. That is just like a backup of backups of backups. Like, we're really not trying to go there.
It will probably be used for restoring wallets or for corrupted state or for a number of other situations where we can't reliably be sure that we have the right state available.
Okay, so basically, so let's talk about restoring wallets as an example, because I think this is really important, right? So if using the stateful portion of this requires having basically like a really clear understanding of the number of signatures that's being used, otherwise you could have a serious security breach, basically, is the issue. You could leak your key, right? You could have forged signature situation. Then if you lose your key and that counter is lost. Basically, any situation where you lose your state counter, you want to make sure that you're using Sphinx Plus as a backup.
Exactly. This is for every case where you can't use this. Because if you can, you should be using the stateful part.
Because it's small.
It's smaller. It's more efficient. It's easier to verify. It's easier to sign with. And it's, I would say, possibly easier to implement in pure cryptography, but the managing of the state is really the complicated and hard part.
You said that the Sphinx Plus option as a signing scheme is about, up to 100x larger than what we're doing with ECC right now.
Yes.
How about the stateless option? What is the size comparison for the stateless option, which hopefully we will be using 99.9% of the time, compared with current signatures in Bitcoin?
Now, the parameter sets that we've chosen for Shrinks are still open for debate. I plan to do a little bike shedding about that myself, but the ones that we've selected now, I think, are very reasonable for the expectations for a proposal into consensus. And they aim for a 5,776 byte stateless signature size. And I'm gonna get this wrong. I think it was something like 538 byte stateful signature.
Okay.
So it's about a factor of 10 difference between the stateful and stateless size. Stateful being smaller, stateless being 10 times larger.
But so that means even the stateful sign is about 10x what we currently have with ECC with elliptic curve signatures?
Exactly. There is a caveat there, though. which is that they're actually much faster to verify than elliptic curve signatures.
Okay.
Yeah. This is why we picked these parameter sets, because it leaves it open in the future for a potential witness discount.
Oh, interesting.
Yes, because they're so much cheaper to verify.
Being able to, in my mind, I was thinking, well, cheaper verification is, great for nodes, but it doesn't change the cost of, the cost of a transaction, essentially. Yes. But you're making the argument that it actually might, because maybe we can change the discounts.
It depends upon whether the network values the cost of verifying signatures versus the cost of storing witness data in the long term in archival nodes. If we care more about the compactness of our signatures and keeping the blockchain small, then we would want to modify the parameters, and you can. There's actually a way to halve the size of the stateful signature, and arguably also some decrease on the stateless side, but you could turn this 530-something byte signature down to a 260, 270 byte signature if you wanted to. But doing that would increase verification time massively. So we opted for the faster verification versus smaller signatures.
Why does having faster verification kind of rationalize, a potential deeper discount? Explain
because
that to
the
me.
Witness discounts that can be applied to a signature scheme are commensurate with the amount of work needed to verify those signatures.
Okay, on the verification side. And is that basically why SegWit has the discount? Is it the same?
I believe so. I would have to read up on that.
Okay.
I don't want to spew some nonsense.
Fair enough. Okay. Have you guys batted around any specific ideas for what a discount could look like? Obviously, I assume this will be a very different BIP, but just out of curiosity, are you guys thinking about what kind of discount might be applied to these signature schemes?
I have no idea. This is only a rough first draft, and we expect the parameter sets will probably be changed. We just wanted to pick some relatively non-controversial parameter sets to start with. And then once we publish our ideas to the community, then we can have discussions about what the right way to approach this long term is.
I was going to say, once you get into discounts, things get way more controversial really fast, right? Then people start worrying about spam and other issues.
Yeah. A lot of people think that there's really no way to do post-quantum signatures without a witness discount because they're all huge, with the exception of isogenies. But then isogenies are so slow to verify. So, and this is especially true with hash-based signatures. They're really huge, but they're actually so fast to verify compared even to Schnorr. The cost per byte to verify a hash-based signature is tiny, especially for the stateless side, because the signatures are huge, right? So even if you have a decently large verification cost, dividing by that huge byte size gives you a very small cost per byte.
So a discount, a signature discount is one way of potentially handling this increased size issue, which it sounds like is made improved by shrinks, but not fully solved by shrinks.
Exactly.
Is that accurate?
Yeah, we've done our best to provide the optimal trade-off space for wallets. And wallets that can manage state can use the stateful side and can get very small and efficient signatures. Those that can't, or wallets that are recovering from an emergency scenario, who've lost their state, then they can fall back to the stateless side and still be able to rescue their money.
Would another way that we could potentially deal with the sizing issue be something like Benedict's signature batching, right? Is that sort of the other way that we could potentially solve this?
I don't see any way that you could do that kind of batching on Bitcoin without a very significant consensus change.
Like a serious software, like a zero-knowledge proof.
Yeah, because you can aggregate signatures using a ZK Stark or a Snark or a PQ Snark or something like that in a way that makes it very easy to verify for light nodes. But ultimately, the ideas that Benedict were proposing, I believe, would still require archival nodes to maintain a record of all those signatures, because otherwise, how do new nodes bootstrap unless they're verifying the ZK proofs?
Yeah, you'd need to have special archival nodes. You'd be introducing a new player into the whole game theoretical system.
Yeah, we're not trying to go for that. We're just trying to go for the minimal, viable cryptographic proof of concept that would work on Bitcoin without any major consensus changes like, witness discounts or ZK Starks or anything like that. I think that in a situation where we have a sudden quantum computer appearing and we need to start using post-quantum cryptography ASAP, the ability to use 530-something byte signatures will still make Bitcoin survivable.
All right, guys, taking a quick moment to thank my new sponsors of the show. First off, the one and only Layer 2 Labs, pushing forward research and development of drive chains. Drive chains were first introduced as a soft fork proposal to Bitcoin, aka BIP300, BIP301. These BIPs essentially propose a bridging mechanism between Bitcoin and Layer 2s that are incentive aligned with miners, and they've gotten a ton of attention over the last couple of years. If you're curious about how drive chains could work in practice, though, check out layer2labs.com and download their alternative front end to Bitcoin Core. It lets you play with drive chains and see how they actually work in real life. I'd also like to introduce Hashi, an alternative primitive to traditional L2s that allows users to execute a wide range of Bitcoin DeFi activities without having to trust a federated bridge. With Hashi, Bitcoin is controlled by an MPC wallet that requires a quorum of proof-of-stake validators on the SUI network to execute Bitcoin transactions based on the validity of smart contracts. At least a third of the staking power of the SUI validators network is required to execute these MPC mint and redeem transactions, which is a substantive improvement in trust assumptions relative to other L2s or sidechain bridges. Hashi's commercial team is also stacked, including a crew of former builders from the crypto division of Meta. I think we're going to see a suite of super competitive Bitcoin DeFi products built with this protocol, so definitely check out the Hashi page on sui.io if you're curious. Last but not least, shout out to Bitbox. Bitbox is one of the easiest and most simple to use Bitcoin hardware wallets on the market right now. If you have friends or family members that you want to make sure stay safe and use cold storage, but maybe they're not the most Bitcoin native people in the world, I highly recommend checking out Bitbox. They're completely open source, no compromises on security, but they're also super easy to use, really intuitive UX. Plus, you can use them with concierge multi-sig services like Unchained, which I'm personally a big fan of. If you want to check out their hardware wallets, go to bitbox.swiss and use code BitcoinRails to get a discount. All right, back to the show. So we've kind of covered sort of the deep underbelly construction of SL root. Should we go into a little bit more deeply, and we can kind of pull up a new cue card, but should we go into a little bit more deeply about how the stateful piece of this works?
Definitely. I think the stateful part is the far more interesting part because it's the novel part that we propose in Shrinks.
So all of this basically is Sphinx Plus, which was created by DJB, not for Bitcoin. It's used in other contexts. It's NIST standardized. You know,
it's pretty uncontroversial.
It's uncontroversial, but it's quite large. And it was the inspiration. Essentially, Shrinks is sort of an adaptation of this whole situation.
Mm-hmm.
Okay. Shrinks uses that piece of it as a backup. But really, we want people to be using this stateful side most of the time.
Yeah.
Let's kind of dive into the underbelly of the stateful side.
Absolutely. So this is FXMSS, the flexible extended Merkle signature scheme. It's actually a lot like taproot Merkle trees in a sense, because the tree structure is chosen by the signer. So it starts with a set of Winternitz keys. So maybe before we describe FXMSS, should we describe Winternitz?
Yeah, let's go for it.
Okay, I'm going to actually change the card around then so we don't get too confused. Let's do one for Winternitz first.
So XMSS is made up of of a bunch of mini Winternitz signatures, a bunch of mini signatures called Winternitz one-time signatures, and we are going to just quickly explain how these signatures work.
Right.
Okay.
We start with a bunch of secret pre-images, which I'm going to draw as little circles here. I'm going to do, say, 5 of them.
Okay.
Now, each of these, you hash them once.
Is 5 a real number, or this is a theoretical number?
This is a toy example. With a real Winternitz key, you would be looking at either 16 or 32 or 64 different pre-images.
Okay.
Right?
Got it.
Okay, so you've hashed each of these, and I'm just going to draw a little hash
And these
function.
pre-images theoretically are like essentially the inputs that make your key, effectively.
Yes.
Okay.
Yes, they are the secretest part of the secret key.
Right. That is like the randomly generated, like that is what the wallet is generating to create your key. Those are like the numbers.
Well, if you actually want to be more specifically accurate about it, in Shrinks, we generate each of these from a common seed.
Oh.
Well, otherwise you would need to store them all, which would be prohibitive,
Which
right?
would be annoying.
Yeah. This is actually where we could talk about the shrink secret key a little, but for now, just think about this as like a secret seed. Maybe it comes from your seed phrase. It's derived from some deterministic function. Anyway, this is a secret part that no verifier ever sees, and it generates all of these different pre-images. And okay, so this is one hash iteration. Each of these we call a chain because, as we're about to see, we hash them again.
Ooh, hashes on hashes.
Hashes on hashes. And then again.
Okay.
And we keep doing this for a number of steps.
How many times do you hash on hash?
Is
it standardized?
Yes. In the parameter scheme that we use, 16.
Okay.
We call the length of this chain a parameter called W, also known as the Winternitz chain length. Each of these is a chain.
Okay. So a chain is a chain of hashes of hashes.
Exactly. If you actually want to be more technically correct about it, I think it's something like an iterated hash function. But anyway, you can think of them more intuitively as chains of hashes, where each step in the chain is a hash function evaluation.
Okay.
So you're hashing the hash of a hash of a hash.
Okay.
Eventually, at the end, you get to the tips of each hash chain. These are each tips. I'm just going to call that here. I don't know if that's a technical term. That's just what I call them, by the way.
Great. I love it. Let's make it a thing.
Now, in order to create the Winternitz public key, you then hash each of these together into a single 16-byte value called the public key.
Okay.
Now, in order to create a signature with this scheme, remember, we are only signing a single message here. You can only sign a single message with this scheme safely. First, we take a message and you map it through a function into a set of indexes. Note that our chain length W here is 4.
Okay.
We would map this to a number between 0 and 4.
Okay.
Exclusive. So it would be 0, 1, 2, or 3.
Okay.
So let's just say we choose a set of indexes. That's what those message numbers are. Those numbers between 0 and 4 are called indexes. Let's just take an example message that maps to, say, 1, 3, 0, and 2. And we'll get to why there's only 4 numbers in a second here. Like, we have 5 chains. Why aren't there 5 numbers? You'll see. You'll see. So
it's an off by 1 error.
Yeah. You'll get to it. So the first number, the first index is 1. So you hash your preimage once, and you reveal this node as part of your signature.
Okay.
Next one is 3. You hash your preimage 3 times. 1, 2, 3. You reveal this node as part of your signature. And then 0 times. You don't hash your preimage at all. You just reveal it. That's part of your signature. The next one. 2. You hash your preimage twice. That's part of your signature. Right?
Okay.
These hashes form the Winternitz signature.
I see. And this is why it's one time only, because if you have too many constructions of this, you can kind of like do some magic and figure it out.
You can think of the attacker as being able to see this, and this, but they can't see anything beneath those hashes in the chain, right?
Yep.
Just like here, they can't see your seed. Here, they can't see any of these intermediate hashes or the preimage. And here, they can't see this preimage. The attacker would be able to forge a signature if you revealed a different one. So for example, if this index and this index were changed slightly, then the attacker would be able to see this preimage, and this would give them enough information to forge a new signature.
Makes sense. Okay.
Yeah.
So this is why these signatures are one time only. And then again, so you take each of these one time only signatures, and then we'll get back to how we smush them all together to make the larger, bigger Sphinx/Shrinks signatures.
The missing piece that I haven't discussed yet is this chain, which I haven't used yet.
Okay.
This is called the checksum chain. There's actually multiple checksum chains in the real Winternitz scheme, but I'm just using one here for simplicity. If you were to use this as your signature scheme as described, it would be very easy to forge, right? Here's why. Just change 2 to 3 and then reveal this one. The attacker already knows this, right? They could very easily just iterate the hash again and reveal that as a signature on a different message.
Oh, so this is a safety precaution.
Yes, this is essential to security. In order to make this secure, we add something called a checksum, where you sum all of the indexes. So 1 plus 3 is 4 plus 2 is 6. You would then subtract that from the maximum possible checksum. By subtracting it in this way, you make it so that an attacker cannot just iterate another hash function, iterate one of the hashes to get a new forged signature. Because in order to do that, they would have to decrement the index on the checksum chain.
Got it.
And that's not possible because you can't, in theory, you can't just invert a hash function very easily.
So this is the key answer to why there's only 4 numbers here, critical to security. Don't leak more information that could potentially create signature forging situations.
Exactly. And in this particular instance, I think the maximum checksum would be 3 times 4 is 12 minus 6. So actually, I didn't do my math correctly with the way that I had the lengths of the chain. There should actually be, I think, like 6 nodes in each of these chains, but I'm just going to ignore that for now.
All right. Okay, so we've now covered Winternitz one-time signatures, you guys. Nice little close-up shot of that. Okay, and now this is the perfect opportunity for us to go back to, did we have the X?
Oh, before we leave this, actually, I'm just going to mention one more thing.
Okay.
This is called Winternitz with tweaks, Winternitz TW, or also known as Winternitz Plus.
Oh, that's right.
It's known as Winternitz Plus in the NIST standard, but Winternitz TW in the paper.
Okay.
I'm not quite sure of the difference, but essentially this is what's used in the stateless part. The stateful part uses
the stateless part of shrinks.
Yes.
Or the stateful part of shrinks.
The stateless part.
Oh, the stateless
This
part.
is what's used in the stateless part. This is the part that's been standardized by NIST.
Okay.
In the stateful part, we use basically the exact same scheme, except we use a different technique for the checksum.
So this is where you guys got creative. This is where like Jonas got creative.
Well, actually, this was Mikhail's original invention, I believe. He worked with Andreas Holsing to create a variant of Sphinx called Sphinx+C that uses a slightly different version of Winternitz that has smaller signatures and better performance.
And the reason to do these optimizations is just reducing size further and further. This is just like another way, another tweak that they made to this scheme in order to decrease the size of the signature.
We could have reused this in shrinks, but we were thinking, we're creating something from scratch for Bitcoin. Why don't we make it as efficient as possible? We'll use the best schemes available to us.
Word. All right. Amazing. All right. Okay. So let's go. Now we have, so the Winternitz one-time signatures are kind of like the base building blocks other than fours, which is sort of a separate issue, that sort of foundational piece that we talked about. Okay. So now you have these Winternitz one-time signatures. I think we kind of understand sort of the kind of very deeply now, the math behind those. FXMSS. This is also used for the stateful portion of shrinks, which is really the innovation that you guys are proposing. Okay.
Yes. Okay, so there is 2 different ways of looking at this, and I'm going to bisect this into 2 different ways that the signer could generate their key pair. The first, I'm just going to block this off and call this UXMSS. This is the idea that Jonas proposed with shrinks initially. It's called unbalanced XMSS. In this situation, you create a bunch of Winternitz keys and you arrange them into a Merkle tree laid out like so, where you have an unbalanced tree with a bunch of Winternitz keys hanging off of a single long spine.
Oh, so this unbalanced key basically is this specific shape, and we'll just show it, of how these Winternitz signatures are essentially connected in a Merkle tree.
Precisely. This shape is called an unbalanced Merkle tree. Each of these leaves is a Winternitz +C key.
Okay.
That stands for Winternitz with compression. That's the variant of Winternitz that I teased you about a second ago, that Mikhail and Holsing created.
So Mikhail invented this particular scheme.
I don't want to say that for sure. I would love to talk to him and confirm that, but I think so.
Okay. Got it. Okay. So this is the structure of how these Winternitz, compressed Winternitz, which is sort of another, we're just adding optimizations on optimizations. We're trying to get this thing as small as we possibly can. That's the idea.
This is coming close to the floor of how small hash-based signatures can be, because Winternitz, I believe, is like the smallest hash-based one-time signature that we know of, as far as I know. And the variant WOTS+C specifically pushes that limit quite close.
And just for clarity, this specific construction of a Merkle tree is also designed for sizing purposes. It's just another optimization of making it smaller and smaller. I mean, literally every single piece of this is basically how tiny can we make each little piece of the signature, essentially.
Now, the reason why we lay it out this way specifically, and to get that sizing like you're talking about, that compactness, is because in order to create an XMSS signature, what you do is you select one of your Winternitz leaves, and you use it to sign a message, and your signature in XMSS is just a Winternitz signature appended to a bunch of Merkle authentication nodes. So are you familiar with Merkle trees?
Mm-hmm.
By the way, this is not to proportion. This signature is actually much larger than this part in most cases.
Okay. This is just to fit the letters in.
Yeah. It actually changes because notice that when you're issuing a Winternitz signature, you just use this node. And in order to provide the Merkle authentication path, that's this component here, all you need to do is provide this hash node of the Merkle tree. Just this one. That's 16 bytes. That's all the overhead that you need on top of the Winternitz signature.
Okay, so this is a perfect opportunity. So this particular signature scheme, we only need 16-byte hashes to execute this, which is unusual, right? I mean, usually in Bitcoin, we want longer bit length hashes than just 16 bits.
Well,
correct?
16 bytes.
Bytes, excuse me.
Yeah.
Excuse me.
And this will be a very interesting discussion. I want to save this actually for after we've gone through BXMSS, which is a little different.
Okay.
Yeah. But absolutely put a pin in that because it's worth discussing.
Put a pin in it. 16-byte hashes. Unusual. We're coming back to this.
Now, just again, you need a Merkle path and a Winternitz signature. That is all the XMSS signatures are. I mean, there is one or two other small things sometimes, like for Winternitz C, you actually need this tiny little 2-byte counter on top. That's to fix the checksum problem that we were talking about before.
Okay.
But 2 bytes is a very, very good trade-off to make for that. It makes it a lot smaller than a stock Winternitz signature. Okay. So this is all that a UXMSS tree is. It's just an unbalanced tree.
This is the original proposal that Jonas put out a very long time ago, but it's since changed. Is that the implication?
It took some convincing, but I think I talked them into changing the structure to be flexible, which is why it's called flexible XMSS now.
So you don't have to use this shape.
You don't have to. And the other shape that we prescribe is called balanced XMSS or BXMSS.
Okay.
So I'm just going to partition this off now.
So it has to be either UXMSS or BXMSS. In this situation, flexible means one or the other. It doesn't just mean any shape that you want.
It can mean any shape you want.
Oh.
Yeah. That's the interesting part. The verifier, remember, all they see is the counter, the Winternitz signature, and a bunch of Merkle nodes.
Okay.
To recompute, ultimately, the stateful root hash from back here. That hash there, make sure you can see that on the camera.
Yep.
That hash is this node.
Okay.
Maybe I should write that explicitly. That is the stateful root hash of the public key in shrinks. All you do to verify a shrink signature is just recompute that from the Winternitz signature and those Merkle nodes.
Okay. All right.
Yeah.
Verification. Easy peasy.
Yeah. It's the same as it works in SLH, DSA, and Sphinx.
Okay. All right. Okay. So BXMSS, you said
Yes.
was like an ordained shape also?
Yeah. We prescribe...
You can use anything, but you suggest either UX or BX. Is that fair?
Yes. We strongly recommend people stick to these two shapes for two reasons. First of all, security. We're only formally proving security for these two schemes.
Oh, so the other ones are just Wild West.
If you want to use your own, you can. And we wanted to design the scheme so that it would be flexible enough to permit novel use cases we haven't thought of. And besides that, the verifier doesn't really need to care what shape of tree you generate, as long as you commit to a tree.
Okay.
As long as it can verify that your signature matches that root hash commitment.
So you can we'll be able to verify any shape, but you guys are only signing off. You're only like priesthooding UX and BX shapes. Okay. So what's the BX shape?
The balanced XMSS tree is kind of what you'd expect from the name. It's a balanced Merkle tree. It's pretty much
Which is normal. This is like what we learn in school about Merkle trees.
Precisely.
This is what we think they look like when we think about them.
Exactly. And it has a specific depth.
Okay. What's the specific depth, out of curiosity?
But we actually don't specify it. But any given BXMSS tree can have a different depth.
Okay.
So for example, you could have a BXMSS tree of height 2, which has 4 nodes, 4 Winternitz keys. You should probably write that. Each of those leaves being a WOTS key, but you could extend this to a deeper tree. You could have 8, 16, or any power of 2. We recommend, for balanced XMSS signers, 2 to the 20 leaves. So that's about 1 million. Okay. Yeah.
All right. Okay. Anything else that we should know about FXMSS, specific portion of the signing scheme?
The main thing is the trade-off, what you get between the two.
Okay.
So for UXMSS, what you get is a key pair with 256 possible signatures. So you can sign up to 256 different messages. And each of those signatures will use a Winternitz leaf, one layer down from the previous one. Now, think about what this means for your signature size. Because remember, the nice thing about this one up here was that we only needed to provide a single Merkle node in order to authenticate this WOTS key against this Merkle root. But what if you do this one? Well, then you also need to provide this sibling hash and this one.
So this actually ends up creating a bigger signature.
Yes. Every time you create a new signature with UXMSS, the next signature will be 16 bytes larger.
So why did Jonas initially propose it that way?
That's because this gives you the best possible size. And most Bitcoin keys are only used once.
Oh, I see.
Which gives us the best possible trade-off for Bitcoin.
Okay.
And if you want to reuse a key, you can. You just end up using the next leaf down. But that makes your signature bigger. So you'd ideally not want to do that.
What's the sort of benefit then of using BXMS? What do you get from a Bitcoiner's perspective of using BXMSS?
Well, first of all, you get many, many more signatures. Like with 2 to the 20 leaves, for example, you get 1 million signatures. That's more than enough for most use cases.
Whoa.
If you're posting 1 million signatures on chain, you have other problems than size.
That'll take you some number of years.
It'll take you a good few seconds to generate that many XMSS keys, I think. Or sorry, that many Winternitz keys.
Well, I mean, to use them, it'll take you. You'd have to really fill some blocks.
Oh, yeah.
Yeah.
And we've thought about how this could be used for Lightning. And this is one particular potential use case for it, because Lightning signers often repeatedly sign many, many messages.
Was that the argument that you made to Jonas to include BXMSS, is that it might be useful for Lightning?
It's useful for many different things. I mean, some people do need to reuse addresses for practical purposes, like custodians.
Proof of reserves.
Yes, exactly. You need sometimes to have a whitelisted address that you can send to again and again. And that use case, we want to still allow that in a post-quantum world. And BXMSS is one thing that lets us do exactly that.
Okay, so that's really important, because I think a lot of people are assuming that we're going to give up the ability to to safely reuse addresses. And specifically, I think the most common example of why that's a problem has been proof of reserves. You're basically telling me that, Alex Leishman can sleep easy with BXMSS because, River will be able to continue doing their proof of reserve.
I don't know too much about proof of reserves myself. And in fact,
it just requires spending, right? You have to spend from something that you then will have to spend again from.
I guess so. I'm
Like,
sorry, I'm not too familiar with that.
Can you spend from a wallet twice safely?
Yeah.
That's my question.
Oh, 100%.
Yeah, that's the key
100%.
thing. Okay, so if you can do that, then you're probably good with proof of reserves.
BXMSS is mainly aimed at signers who reuse addresses or for off-chain protocols.
Okay.
Where sometimes having a constant size signature is important. That's the other thing about BXMSS that's really nice. Your signatures are always the same size, because look at this one. If you have a Winternitz key at this position, you need to provide this leaf and this node in the signature. 2 nodes, 16 times 2, 32 bytes, plus the Winternitz signature size. But if you picked this leaf, then you would need to reveal this leaf and this node. Again, 16 times 2, 32 bytes. It's the same signature size no matter which leaf you use.
So we're really kind of getting to what I wanted to sort of actually wrap up this conversation with, which was kind of talk about the functionality trade-offs with using hash-based signatures. And it sounds like maybe some of that functionality is preserved by using BXMSS instead of UXMSS. That being said, before we go down that rabbit hole, is there anything else that we want to cover to kind of explain how this signature scheme works? Maybe we can kind of do a little concluding board.
Maybe it'd be worth connecting it back to the public.
Let's connect the dots. Should we connect the dots? Okay. So in conclusion on how this scheme works, is there anything major any major component that we've missed of the signature scheme to wrap it all together?
Well, we have the 2 different, I think if we go back to the public key format, we can maybe.
Yeah, let's look at this and see where we're at.
So if I actually just hold the card right here, you can see that the stateful part exists over here in parallel to the stateful part. And the stateful part can be either of these 2 shapes.
Okay.
And the shape of the 2 trees is chosen by the signer, the person who creates the key, and it's chosen at key generation time, and it is fixed forever once you've generated the key.
Okay. That makes sense. Okay. You say that like that's a really important note.
It's very important for wallets. If you were to, say, generate a UXMSS key, and that would be your stateful root hash, and then you were to, say, import that key into a different wallet, this would be a misuse of the scheme, first of all, because you'd be needing to move your state over, which is a big faux pas and very dangerous.
Okay.
But if you tried to, and then you tried to, say, generate a BXMSS tree on the stateful side instead, this could permit loss of funds.
There's so many ways this can go wrong.
There's so many different ways that you can misuse signature schemes. So it's very important to be very explicit about what the invariants are and how you're allowed to use them.
So we have to be really, really careful about how, and this is a wallet developer problem. Users will not have to worry about these issues outside of just making sure that they're choosing wallets that know what they're doing.
Yes, this is a matter of helping developers come to grips with new family of cryptography.
How difficult do you think it's going to be to get wallet developers, really boned up on this and make sure that they don't screw things up for users?
I think the first stage of integrating shrinks into any wallet is to integrate just the stateless part, which is actually very easy. And we've made it very easy with our design because you don't need to do any bespoke cryptography to do it. You can just use stock SLHDSA libraries with tweaked parameter sets. All you need to do is change a few constants and you get the exact scheme we use in shrinks. Then, once the developer feels confident enough and understands the stateful risks and trade-offs and how to use it properly, then they can go about implementing the stateful part.
So you actually recommend that the implementation of this cryptography at the wallet level be done in stages, right? To make sure that the developers are sort of like getting comfortable with what they're doing. It's sort of like one step at a time in it.
Yeah, I'm not sure how I would go about recommending integrating shrinks just yet. We're not at the stage of defining like wallet level BIPs. Like we have nothing for how to derive shrinks keys
Those
from
will be some important BIPs.
Yeah.
Like these are going to be pretty critical BIPs actually, like stipulating all of these potential dangers and really being careful about, educating wallet developers on how to do this.
And then there's the matter of hypertree pruning for hardware wallets, which is a whole nother beast. It involves modifying the stateless algorithms, which until then have all been purely standard NIST approved. and how all of these different modifications and customizations, like the shape of the stateful tree, whether you use pruning on the stateless tree, these are all things that'll have a lot of interplay and will need to be very well and thoroughly standardized.
Okay, so before we get into what I, again, want to wrap up on, which is the functionality conversation, which I think is important to discuss. Dan's brought it up. Benedict's brought it up. Is there anything left that we haven't covered that's sort of like major? Oh, fours. Let's give fours a try. All right, so fours, and again, just to remind people, what is the function of the fours signatures in all of this?
Fours, their job, the fours key pairs, there's actually a lot of them here I haven't drawn, but you can imagine if you descend through this hypertree all the way to the bottom, it's got a very large number of fours key pairs. And when you're making a signature, the scheme pseudo-randomly selects a single fours key to sign the actual message that you're trying to sign, like a Bitcoin transaction or a certificate or a document or firmware or something. And the fours key pair is what signs that message. Now, let's go over to a new card because I think we're going to need more space for this.
New card for fours, you guys.
Yeah.
All right, let's do this. Oh, here we go. Is this there we go. Will do.
Okay.
Here, let's put this one behind so that we can. Okay, there we go. Okay, so fours.
Yes. So
the last sub-signature scheme used in Sphinx/Shrink.
Yes, this is from SLHDSA and Sphinx. This is standard NIST stuff here that we're about to talk about.
Okay,
so this is
put big
old
fours
ground
right there.
Yeah, good. Thank you.
All right.
Fours. Fours stands for Forest of Random Subsets. And the name forest, I think, is very apropos because you begin by generating a forest of Merkle trees. I'm going to do 3 here in this example.
A forest of Merkle trees.
Yes.
I know we're doing 3 as a toy example. How many Merkle trees are we talking about in a 4 signature?
Oh, I believe we use 10 trees of height 13.
Okay.
In Shrinks. It might be the other way around. It might be 13 trees of height 10, but I'm not sure.
Okay. And basically, I mean, let me know if I'm getting this right, just as a general simplification. Essentially, this is truly different cryptography in the sense of it's different math tricks to protect information.
Yes, Fours uses a very different kind of combinatorial problem that the other signature schemes that we've talked about before don't use. The assumption is technically called interleaved target subset resilience.
Okay.
Yeah. ITSR. And I have a great analogy to describe why it works, but we'll get to that in a second. Let's first describe how fours works at a simplified level. So each of these, I should probably draw the actual pre-images here. Each of these little circles at the bottom are pre-images generated by the signer secretly. Always from a seed, by the way.
Okay. Same as with Winternitz, there's a seed. Okay.
Exactly. So I can draw it here actually, and there's a secret seed that just generates all of these and generates all of these. And
there we go. Right. You don't have to keep track of all these little roots. Okay.
Precisely. So these are all secret pre-images. Mm-hmm. Like that. Okay. Each of these pre-images is hashed to get this set of leaves for each of the Merkle trees. And of course, then you hash and combine them together into a set of root hashes, the roots of the trees. And then those are again hashed to form the forest public key.
Okay.
This is the thing that the hypertree back over here.
Oh,
this is the thing that the hypertree signs. That square right there is the exact same thing as this. This is the forest public key.
At some point, I think I'll make a collage of how all of these whiteboards fit together. Maybe we'll add that as a special image on the pod. Okay.
If you do it with vector graphics, you can make it zoomable even.
Yeah.
So you can zoom all the way in down to the lowest levels. But anyway, what you do in fours is you take a message and kind of like in Winternitz, you map it to a set of indexes. In this case, each index is going to be a number between 0 and 4 exclusive. So you map it to a set of indexes between 0 4.
Okay.
So for example, we could choose another random message. Let's say we map to indexes, I don't know, 2 and 3 and 0. Notice there's one index for each tree.
Okay.
All right. Each index that you map the message to selects a particular preimage from each tree. So the first one, 2, 0, 1, 2. We select this one and we reveal it as part of our signature. Well, we're not done there. Unlike Winternitz,
I was going to say, it sounds similar to Winternitz, but different shapes.
Exactly. We need more in order to authenticate it, because just that preimage alone tells a verifier nothing. You also need to reveal this node and this node. Those are the Merkle authentication nodes needed to eventually recompute this value here.
Okay.
And then you do the same for every other tree. So 0, 1, 2, 3, we reveal this preimage. And of course, to authenticate it, we also must reveal a Merkle authentication path. So we need these two nodes.
Taking a wild guess here, another difference between kind of FOR's cryptographic constructions and Winternitz is that you don't need a checksum.
No checksum is needed.
There we go.
Yeah, the Merkle authentication paths provide all of the authenticity that a verifier needs. And then 0, of course, we do the same thing here, revealing these nodes there. So together, if you just highlight all of these circled nodes and give those to the verifier can check that this is in fact a preimage of this Merkle tree by hashing it with these two nodes and recomputing for each of the trees their roots. Then they hash them all together to recompute the FOR's public key.
Question.
Yeah.
Why with Winternitz you can only use once, but this you can use potentially up to, I think you said maybe 10? Is it just because there's just more of these numbers and it's just harder math you just need more information basically in order to figure out the key?
The fundamental problem that you're trying to do, if you're trying to forge a FOR's signature, let's say you're given just one signature, right? This one that we've just drawn here. In order to do that, you have to find a message where each of the indexes selected by that message, remember, because you're mapping the message to a set of indexes, that message must map to the same indexes that the signer has already revealed. Because you just know, as an attacker, this preimage, and this preimage. And in order to forge a signature, you have to reveal the correct preimages for your signature message. So if this is a transaction, this would be a lot longer, by the way. This would be many more numbers, and the numbers would be much larger. But the key point is that you need to find a message that overlaps with the preimages that have already been revealed in previous signatures. If I were to reveal another signature, so let's say we sign a second message. Let's say we sign 3, 1, 0 again. Now I reveal 0, 1, 2, 3. I reveal this one, this preimage. And that means I also need to reveal this node. And this one has already been revealed, but I'll reveal it again because it is part of a complete signature. And 1, that selects this preimage. So I reveal this preimage and this node, and I must also reveal this node. And for the last one, it's the exact same, so I don't need to change that. So now the adversary has a couple more preimages, right? They have this one, that's new, and they have this one, that's new. So now, if the adversary were to find a message that is any combination of these sets of indexes, like say if you were to just like swap these two around, then you could sign the message 330.
I see.
Yeah, you could also sign the message 330, or sorry, 210, or any like mixing and matching and combining of the different indexes that you've selected.
What do you think are the trade-offs between FORs and Winternitz? Like, why do we use Winternitz sometimes and FORs other times?
Because FOR signatures are huge, man.
Oh, really?
They're huge.
They're just big.
They're, I believe, like several kilobytes.
Oh, man.
Yeah, man. A big section of every SLHDSA Sphinx signature is the few time signature, because you really need that extra size in order to get the few time property.
And I think Jonas even confirmed, I asked this question on the podcast with Jonas, and I think he said sort of by definition, like signatures that you only use once are always going to be the smallest by definition. Yeah, that makes logical sense. Okay.
They give the most trade-off in terms of like signature budget, because obviously they throw away your entire signature budget, save one, and then that's as low as you can go, so you can't make any more of a trade-off.
It's like a law of physics.
Yeah.
All right. Okay.
Now, so this all is dependent on the mathematical probability theory behind this question of, how frequently will a message overlap with a set of pre-images that have already been revealed? That is the target, or that is the interleaved target subset resilience problem. The interleaved part comes from thinking about this problem in the context of many FORS keys. Because remember, there are trillions of these keys in a single SLHDSA key.
Whoa.
Yes.
Oh, wow.
So there's actually trillions of forests. Now, maybe
is that where most of the size comes from?
No.
No, it's the millions of Winternitz signatures.
Yes. There's one, if we go back to this, there's only one Winternitz signature per layer. So there's one here, there's one here, and there's another one here. This is an example with 3 layers of XMSS trees. You could even draw the layers like right here.
Okay. Yeah. All right.
3 layers means 3 Winternitz signatures plus a FORS signature. And that's basically all that a Sphinx signature is. It's just a concatenation of a FORS signature and a Winternitz signature and then another one and then another one.
Basically, we're using Winternitz for their size, and FORS we use as a sort of like foundational base extra budget option.
Yeah. I'll correct myself there. Actually, what I said a second ago, it's concatenation of FORS plus a bunch of XMSS signatures. Because remember, we also need the Merkle paths. I'm sorry, could you repeat the question?
No. Yeah, I was just going to say, like, essentially, like in a nutshell, we're using Winternitz as much as we can, but then we use FORS for this just little extra budget at the bottom, and we trade off the size for it. Is that essentially? Exactly.
It gives us this stateless property where security degrades slowly rather than suddenly. And that's very important because if you were to use Winternitz at the bottom and then you were to reuse a Winternitz key, you're screwed immediately. And an adversary could very easily forge signatures.
So you want a foundation of something that isn't used only once.
Exactly. And that is FORS.
There we go.
Yeah.
FORS.
Now, maybe I should...
we did it. Should we go back? Anything you want to say about FORS?
There's one more
final thoughts on FORS?
It's a little intuition game here, a little example or analogy. You can think of the different trees as, say, products in a grocery store. Each of these trees has a collection of different products that all look the same. Say, milk. Each of these is a different brand of milk, right? And say this one, this is cheese. Each of this is a different brand of cheese. And imagine in this grocery store, imagine that every one of these products looks identical to the consumer. And the consumer just chooses effectively randomly.
Okay.
When they're going through and shopping on their grocery list, right? Each time they find a product on their list, and they buy a random product from any arbitrary brand. The next shopper comes through and does the same thing. And this is analogous to signing a second message, for instance, right? These products are chosen randomly. Sometimes they like overlap and collide, like in this case where we signed the same index.
Right.
And this is a case where 2 customers buy the same product
twice randomly.
Just by random luck. Now, the probability question that you want to answer here is what's the probability that the next customer is going to buy one of these circled products that the other customers before them already purchased?
Okay.
And you can compute this probability, and based on it, you can construct an estimation of the security of this system against forgery, against an adversary who's just repeatedly trying to find messages that overlap with the ones that have already been signed.
Basically, like how many tries does an attacker have before they could effectively brute force this?
Yes. And Shrinks and Sphinx are designed so that that probability is less than 2 to the power of 128 or more. Or actually, I should say,
which is a security assumption we like in Bitcoin. That's like the number that we like in Bitcoin.
Yeah. 128 bits is the security level of SEC-P256K1 against Pollard row attacks. So we're aiming for that same security level with Shrinks.
Okay, there you go. Okay, so we basically want to meet the security level of our existing signature scheme.
That's the classical security. Quantum security is a more complicated beast
but just for hackers, quantum aside.
Exactly.
All right. Okay. Yeah. Well, this was we really did it. We really went for it with this.
And if you can understand all of those little subschemes that we've just gone through, then you understand almost all of Sphinx and shrinks.
This was quite comprehensive. I thought that this was an ambitious project for us, and I think that we pulled it off. I think Jonas will approve of this.
The nice thing about hash-based signatures is that if you break them down into their components, it's really just Merkle trees the whole way down. Like, if you notice that almost every one of these diagrams has a Merkle tree on it.
I mean, we love Merkle trees. Merkle trees are great.
Exactly. It's just Merkle trees. It's forests of Merkle trees. It's Merkle trees signing other Merkle trees all the way down to the bottom.
Well, I think that we've done a great job breaking the signature scheme down to its absolute guts. Anyone who's still here hanging on to this, you are now an expert in Sphinx/shrinks, the potentially new post-quantum signature scheme we're going to have in Bitcoin, which is a big deal. Any final thoughts? And again, we don't have too much time, but any final thoughts you want to add to this design, or anything that you want to note on this design that you guys are proposing? And then I may really quickly ask you some functionality questions.
Why don't we go into the functionality questions?
So, I mean, the main thing that I just want to kind of make sure that we're, in fairness, making sure people understand is, what are the functionality trade-offs with this type of signature? Like, what are we giving up that we currently have in Bitcoin with elliptic curve signatures that we will not be able to do with these hash-based signatures, or specifically with shrinks?
Well, the first and biggest one is the algebraic structure that we have with elliptic curves is completely gone here, because hash functions don't have any linearity. They don't have any kind of way to add two hashes together in a way that's homomorphic. So you can't do fun stuff like bit32 public key derivation. So if you're given a shrinks public key,
so
like
HD
this,
wallets, you can't do.
You can do HD wallets. You just can't do public key derivation from a different public key.
Okay.
The technical term for this is re-randomization. You can't take an existing shrinks key and transform it into a different valid one that the original signer can still use. And that's the fundamental thing that BIP32 does, right?
I was going to say BIP32 essentially allows you to create an infinite number of keys with one XPub, essentially. That's what we're talking about. That's a pretty important core functionality of Bitcoin. I mean, how do you preserve privacy in a practical way without that?
Well, you can have the signer generate a whole bunch of keys. Like, for example, in a software wallet, this would be very easy. The signer would be the computer itself has the key inside its memory, and so it could generate an arbitrary number of shrinks keys from a deterministic seed. And this would give you effectively the same use that we have today.
So there's workarounds, basically, is what you're saying. There's ways to handle this situation.
The hard part comes when you're talking about untrusted parties having access to a single key that they can then derive from, like you can with XPubs today. You can't have a watch-only wallet with shrinks unless it's a single address.
I see. Okay, so that's the issue.
There's a caveat there, which is that if you consider shrinks in the greater context of Bitcoin being used in combination with different signature schemes, like Schnorr or isogenes, then you can actually do that. It's just that the shrinks key can't be randomized, while where the other one can be. So you can still have different addresses, and you can even hide the shrinks public key so they can't be linked unless the shrinks key is used, in which case you do need to reveal it, and that links any other addresses that have already used the same key.
What other kind of like core functionality or like commonly used functionality in Bitcoin are we potentially giving up with this signature scheme as of now until we find creative solution?
There's multi-signature and threshold signature, of course.
I'm very sad about this, you guys. This is a bummer.
Yeah. Now, there's been some very interesting work being done in the shrinks working group on this. There's a couple of people working on using multi-party computation to evaluate shrinks signature algorithms using these untrusted systems where the two parties can compute using shared secrets without revealing those secrets and produce a valid signature, even though they never see each other's secret keys.
Okay, so we may be able to solve this with MPC, which some people would consider slightly less secure than traditional multisig.
Vastly. I think there's a lot.
Very, very less secure than multisig.
I shouldn't say vastly. Maybe it's an overstatement, but essentially it has a lot more moving parts and a lot more opportunity for vulnerabilities. So we would really like if there was a way to do it, but so far we don't think that there is. So we're going towards MPC to see where the ceiling is and how far we can push this idea.
And how secure we can possibly make this thing. I mean, maybe instead of, figuring out how to make hash-based multisig, we figure out just a way to make MPCs more secure. Is that like a hope we can dream for?
I personally don't know that much about MPC. It's actually Boris Nagaev and Alexander who are working on this, and they're doing some very cool stuff. They've got some prototypes working with two-party computation. However, there's caveats, like it's not out-of-the-box quantum secure, and there's got to be more work done in order to get it there.
Would you say that, multisig and XPubs for that matter, probably the two biggest, most commonly used things that we use in Bitcoin today that will be at least like meaningfully changed, meaningfully different using these schemes?
Yeah, 100%, 100%. It's a trade-off space. And unfortunately, the trade-off that you get for the very tight security of hash-based signature schemes is the lack of flexibility. And you can't do fun stuff a lot of the times.
Well, the price of post-quantum security, I guess.
Yeah.
Is that potentially an argument for... I guess in this first iteration, if we add hash-based signatures, we will still keep elliptic curve signature options until it's sort of more clear that, a quantum computer or some sort of potential break in ECC is plausible. Is that the idea?
Yeah, most of the proposals revolve around this idea of commingling the two different signature schemes, classical and post-quantum.
Is this cryptographic agility? Is that the term that we love for this?
I don't know what the
idea?
technical meaning of cryptographic agility is, but that's how I tend to use it in colloquial conversation, where you have, two different keys committed to in the same address, and you can use either of them. And they're both hidden until used. So if one breaks, in theory, as long as the hash function can't be reversed, then you shouldn't be able to forge signatures for that vulnerable one. So if addresses are not reused, and that's a big if, then both schemes should be hidden until used, and you can use whichever one is secure at the time.
So I think it's important for the people to know, we don't necessarily need to switch to this less functional signature scheme, unless or until the quantum computer is like really close to coming. We can migrate to addresses that have both, so we don't have to give up this functionality anytime soon unless we need to, at which point it will almost certainly be a worthwhile trade.
100%, yeah. And the real question that we'll get into then, if we keep talking about that, is what output type do we use? What address format do we use to host shrinks? Because this cannot be deployed as is on the existing script leaf versions in Taproot. It can't be deployed in pay-to-witness script hash, and that is because of the size of the signatures. The signatures are actually too big to fit on the stack.
Well, that this is something close, near and dear to my heart as a co-author of BIP360. This is now I can't not ask you the question. Do you have a take on P2MR versus P2 Taproot 2, which it's not really a fair comparison because P2Taproot 2 hasn't really been truly spec'd out, is my understanding. But do you have sort of a point of view about the output type that we should be adopting in order to use these signatures effectively?
I think any post-quantum output type should be post-quantum, and P2Taproot v2 is not.
Ooh.
It is not. It is. But I respect the...
No, I'm kidding. If it's P2TR, whatever's best for Bitcoin, I'm not attached.
Respect the opinions of people who are pushing for P2Taproot v2 because their arguments are completely valid, but they hinge upon a very key question, which is, can we solve the timing problem? The timing problem is, when is Q day?
Right.
Answering that question would allow P2Taproot v2 to be valid, but until that question can be conclusively answered and then proven on chain in a way that we can trigger promptly, there is really no valid argument for P2Taproot v2.
This is the key point that I know Ethan has also made several times, which is basically that the core problem, all other technicals aside with P2Taproot 2, which basically is just, keeping Taproot as is and then disabling at the time the quantum computer comes, is that we don't know when the quantum computer is going to come. It's a little tricky, a little risky.
And then there's P2Taproot hash, which is a really cool new construction that came out of some work from Boris Nagaev on elliptic curve key recovery from a Schnorr signature. This allows you to do essentially P2Taproot, but behind a hash. So it's kind of a mix between P2Merkle-root and P2Taproot v2, where unlike P2Taproot v2, it's still secure if you sit perfectly still and never spend your coins and never reuse your address. But it still requires the elliptic curve spending path to be disabled. Unlike P2Merkle-root, where even if nobody acts and nobody does anything after it's deployed, P2Merkle-root can still be used safely, in theory. In theory. And there are caveats there, like you can't reuse addresses, you can't share your XPubs with your elliptic curve keys.
With basically with perfect use.
Yeah.
It is quantum resilient and resistant.
In all of these cases, it's still desirable to have an EC disabling fork. But in the case of pay to Merkle root and pay to Taproot hash, there's still a safe place for people to send their funds to. In the event of a quantum emergency scenario. Whereas with pay to Taproot v2, you have to find some way to very, very quickly activate a fork to lock everyone's coins into post-quantum pads. Otherwise, anybody is fair game.
This is going to be a perfect conversation for me to take up with my next guest, Taj, because I know he's doing a lot of work right now on sort of, like ways that we can essentially delay certain kinds of mitigations, quote unquote, until the quantum computer arises. So I'm going to be very curious to ask him what he thinks about the
tripwire and stuff like that.
What?
Tripwire and stuff like that, like activating based on the nums point?
Very well. Various options. I've heard a few. I actually am not familiar with that particular example. Let me know if that's something I should bring up with him.
Oh, absolutely. I mean, there's been many different ideas for how we would recognize when a quantum computer is about to appear. But personally, my philosophy is that it's unpredictable.
I agree.
Nobody
you really don't know.
Nobody knows when a
who's
technological
have when.
revolution is about to occur, right?
If China gets there first, we don't think that's going to happen. But if they do, they're not going to tell us.
Yeah.
Thank you so much, Conduition. This was amazing. I am so happy about our very thorough explainers. And again, for everyone home watching, if you got through this, you are now an expert in the signature scheme. So pat yourself on the back. Thank you so much, Conduition. This was awesome.
Thank you. It's been a pleasure. I'm very glad I got to come on your show. And I've been a longtime viewer, and I'm really liking all that you're doing. And thank you so much for giving an opportunity for me to share shrinks with the world.
Thank you.